I want to continue with the concept of impulse. Now, right before this, we did ballistic pendulum. Okay. All right. So we use the concept of momentum for collision. So I want to look more at a collision, this concept of impulse. So here I have two objects moving toward each other. Okay. So maybe this is like a slow, maybe marble, and this is a huge bowling ball. So I have this one moving slow, this one moving fast. So this is the before picture. This is before they collide. Okay. This is the during picture. So when they collide, okay, they deform a little bit. And we saw that previously where, let's say we had two objects and these things deform, okay, but I showed a video where a ball hits a bat, okay, you can see the deformation where the ball deforms. Okay, so this picture here, okay, so what I didn't show last time that I want to look at this time with impulse is as these things collide, they exert forces on each other. So the large one pushes on the small one to the left. So the large one exerts that force on number one. So that's force one. And the little one is pushing or exerting a force to the right on the large one. And I called that F number 2 because it's the force on number 2. Okay? And the big difference is now these forces can be functions of time. And what I mean by that is, think about this picture here, okay? Before they meet, all right? If I make a graph of force, okay? This is force versus time, okay? So right before they collide, this is before they collide, okay? There's no collision force. That's why force is 0 down here. Right when they start to meet, okay, that's when the collision force begins. So the collision force gets bigger and bigger. And this picture here, let's say they squish as much as they're going to squish, and so the collision force is the biggest, okay? Maybe that's right where the ball here is as squished as it's going to be, right? And now the ball starts to uncompress, okay, move away from M1 starts to uncompress, move away from number 2. And so now that force gets smaller and smaller. So the force can vary with a function of time. And I even gave an example down here of a spring. So let's say I have a car with a spring attached to it. These cars are about to meet. Okay, so before they meet, okay, there's no force, so the force is equal to 0 here. Right when they meet, the spring touches, and then the closer they get, okay, remember from the projectile launcher, the more you compress the spring, the bigger the spring force. Okay, and then when the spring is compressed as much as it's going to compress, that's when the force is the biggest, and then the objects start to move away from each other. So that so the collision force can be a function of time. Okay, now for this collision up here, okay, I have a small object going fast. No, I have a small object going slow. I have a large object going fast. So which of these collision forces is larger? Okay, well, Newton's third law says that the collision forces have to be the same. There's no way for number 1 to push on number 2 any differently than number 2 can push on number 1. So those collision forces are equal and opposite, equal in magnitude, opposite in direction. Okay, so I just drew the same picture here. And again, we can also think of this as this is the side view of the ball and the bat. So this picture could be, this is the ball, and this is the large bat. So this shows the ball deformed. Okay, so they're equal in magnitude. So that's why I did absolute value. Okay, so what we didn't look at the last time in terms of the collision is this collision force. Okay, collision force is a function of time. That collision force changes the momentum, okay, of the ball over a short period of time. So when the ball hits the bat, okay, it's the bat that exerts a force on the ball that changes the momentum of the ball over a really short period of time. And likewise, the ball exerts a force on the bat, okay, which changes its momentum. Okay, so it's a good thing we use the word impulse because we're talking about collisions. And think of a collision that happens over a short period of time. Okay, so think of out of the context of here, where would you hear the word impulse before? Think if you go to the store, you have an impulse buy. Okay, You go to checkout. What do they put in the checkout counter, right? They put like the bag of chips. So you don't go home and read the reviews for 3 weeks on the chips to see whether or not you're going to buy them. Okay, you make an impulse buy. So impulse refers to a collision force happening over a short period of time. Okay, so we want to find the change of momentum for an object during a collision. Okay, so same picture here. Okay, so this one collides. Okay, they collide with each other, and I want to calculate the change of momentum for the collision. Well, I'm starting with Newton's second law. Remember, we're writing Newton's second law in the form of momentum. So multiply both sides by delta t. Okay, that's where I got that to solve for change momentum. All right, so the net force is the collision force. Okay, so the net force is the collision force, and it's a function of time. So for that, I'm going to put in it's a function of time. Okay, and then they'll tell you in the book that usually for a collision, you have no idea what the collision force is as a function of time. We had some kind of graph. Okay, you have no idea the shape of that graph. So what you'll do is instead you'll talk about an average collision force. So there's my collision force, and that bar denote that it's an average. So instead of writing the collision force as a function of time, I'm writing that as an average collision force. So the collision force, the average collision force, multiplied by the time over which that collision occurs, that's called the impulse. And some books use the letter I for impulse, okay, but this book uses J. So it's kind of 50-50 between different books. All right, so here's the confusing part. All right, so when we had the projectile lab, we were in the lab, and sometimes the lab asked you to find the speed. You wrote down the speed, and then after that, it asked you to find the velocity. And sometimes your lab partner would say, well, aren't they the same thing? And we said to tell your lab partner, well, they wouldn't be the same thing because we wouldn't have two different words for the same thing. Remember, speed was a number and velocity was a vector. Okay. Now, here we actually do have, okay, two different words for the same thing. So the average collision force times the time, okay, is a change of momentum, and it's also called the impulse. Okay. Why have two different words for the same thing? Okay, so that's why that's a little confusing. And here's the reason why we're going to have this thing and call it two different words. Okay, now for a collision, okay, when let's say the bat hits the ball, all right, the bat exerts a force. So we'll talk about the impulse of the force the impulse of the bat force that changed the momentum of the ball. Okay, so this quantity is called the impulse. All right. Now, it's a composite of two things. It's a measure of both the strength of the force, right, how big the force is, and the duration, which is the time. So it's a measure of the duration, okay, and the strength of the force. Okay. Now, again, why have two different words? Okay, one there, two different words for the same thing. Okay. Well, the change in momentum, okay, let's say a ball hits a bat. The change in momentum refers to the ball comes in with a certain momentum, okay? Bat hits the ball, now the ball heads out that way with a different momentum. So P initial, P final. So the ball's headed to the right, now the ball's headed to the left, okay? So the change in momentum refers to what happened with the ball. The ball's headed to the right, now it's headed to the left, okay? The impulse refers to what caused the change in momentum. In this case, it was the bat. The bat exerted a force over a short period of time. So here, okay, the force was exerted by the bat. Okay, so that's why we can talk about the change in momentum of the ball. Okay, and we can also talk about the impulse that the bat delivered to the ball. All right, so that's why we can have two different words for the same thing. Change momentum, okay, think about that. That refers to what the ball did. Okay, went in to the right, went out to the left. The impulse refers to what caused that to happen. It was the bat exerted a force over a short period of time. Okay, now the other weird thing are the units. All right, so if I look at impulse, okay, so my impulse, I'll do it over here. So impulse, whoops, right here. So impulse has units of force times time. Well, force is Newton, time is second. So the units of impulse are Newton seconds. Okay. Well, but look up here. Okay. This says that change of momentum and impulse are the same thing. Well, why don't they have the same units? Well, remember momentum, okay? Momentum is mass times velocity. If I look at those units, I have kilograms for mass, and speed is meters per second. All right. Well, if I do this, if I put in, let's see, if I put in another s here and there, okay, so I'm multiplying top and bottom by s, so multiplying by 1, all right. I have a kilogram meter per second squared, okay, so this thing in blue, that's a Newton. And right there, I still have an S. So the units of momentum, which is the red kilogram meter per second, is the same thing as a Newton second, okay? So why use different units? Well, if you're talking about the ball up here, talking about what the ball's doing in terms of its momentum, then you would stick with units of momentum in kilogram meters per second. Okay, so the red units here, okay, units of momentum, you would use to talk about the ball. Ball goes in to the right, goes out to the left. Okay, these units of Newton seconds, the blue Newton seconds, okay, that refers to the impulse. That refers to the bat, okay, exerting a certain force in newtons, okay, over a period of time in seconds, okay, or during a period of time in seconds. All right. So it wouldn't be wrong to give momentum in these units, and it wouldn't be wrong to give impulse in those units. It's just customary that if you're going to give the units of momentum change of the ball, use those. If you talk about the impulse that the bat gave to the ball, you use those. Okay. All right. So I did an example here. Okay. So here's my coordinate system. I picked X to the left because the ball's going to go out to the left. All right. So we had this, right? So the change of momentum was the average collision force times the time. We said that's the same thing as the impulse. Okay. So the impulse is the average collision force times the time. So if I wanted to calculate the impulse that the bat delivered to the ball, all right, you look at this, you say, well, I have no idea what the collision force is. I just know the mass of the ball. You know, the ball came in at 10 meters per second. Bat hit the ball, goes out the same speed. How do I calculate the impulse if I don't have the collision force? Well, impulse is just another name for change in momentum. And I can calculate the change in momentum. That's P final minus P initial. So there's my MV final minus MV initial. And I'm writing these as vectors, okay, with the arrows. Factor out the M. Oops, and okay. And then over here, when I wrote my change of momentum, I left off the arrows. Okay, there's no arrow here or there. And then I'll put in the correct plus or minus sign based on the direction of the arrow. So my change of momentum is MV final minus MV initial. Okay, my V final is 10. Okay, my initial velocity is minus 10 because it's headed in the negative direction. Okay, so that would be the initial speed. Okay, initial velocity is minus 10. Okay, so this gives me my change of momentum. So if I write it as a vector, my change of momentum is 20, and those are the units. Okay, to the left. That arrow shows us to the left. Okay, oh, I'm sorry. It's a positive number here. So the positive number implies the change of momentum is to the left. Okay, well, the impulse is the same as the change of momentum. Okay, well, momentum's 20, so impulse is 20, and it would be okay to write impulse in these units, kilogram meters per second, but a kilogram meter per second we just showed is the same thing as a Newton second. Okay, and since that's positive, it also points to the left. Okay, so look at this picture. Ball comes in to the left, goes out to the right. So the change in momentum, okay, is a positive number, points to the right. So this arrow here, the one that points to the left, that was my positive direction. That arrow indicates the change of momentum of the ball, indicates the force or the average force exerted by the bat, okay, and it also indicates the impulse that the bat delivered to the ball. Okay, so here's one with numbers. So I have a baseball, mass of the baseball, comes in about 90 miles per hour, bat hits the ball, leaves at about 90 miles per hour. Okay, so I went online and I found, okay, well, the ball's in contact for the bat for about a millisecond, 1,000th of a second. So what impulse did the bat deliver to the ball? All right, so impulse is the J. All right, so let's say you look in the book, you say, okay, I want to find the impulse. It's the average force times the time. Well, there's no indication up here what the average force is. Okay, but that's where you have to remember that impulse, okay, is another word for change of momentum. Okay, and that's the example we just did, right? You can easily calculate change of momentum, P final minus P initial. Okay, so again, for this problem, here's my coordinate system. Okay, so P final is change of momentum is P final minus P initial. So factored out the M. So my final velocity is 40. Okay. Whoops. Well, my final velocity is 40, and I said it goes in and out with the same speed. So my final velocity is 40, and my initial velocity is minus 40 because it's heading to the right. That's my negative direction. So V final is 40, V initial minus 40. That's the mass of the ball. Okay, I put this in the calculator, and the impulse, right? The impulse that the bat delivered to the ball would be 12 Newton seconds. Okay, and since it's positive, it's to the left. Okay, now I could also ask, what impulse did the ball deliver to the bat? Okay, so in that picture, okay, if this is 12 Newton seconds to the left, then that would be 12 Newton seconds to the right. So this would be the impulse that the ball delivered to the bat. Just like Newton's third law, the bat exerts a force on the ball. Okay, here the ball also exerts a force back on the bat, and also exerts an equal and opposite impulse back on the bat. Okay, so that's for part A. Part B is, what's the average force that the bat exerts on the ball? Okay, well, you already know the impulse is a number, and the impulse is the average force times the time, so I can just solve this for the average force. So here's the impulse, there's the time. Okay, so that gives me my average force at the bat, and also the average force that the ball exerts back on the bat. Okay, but this is the average force that the bat exerts on the ball, and it's positive, so that means it's to the left in that picture above. Okay, now part C, is what's the average acceleration of the ball? Okay, well, I go back to the earlier chapter, F equals ma, so the average force is equal to ma average. Solve this for A. Okay, I know my average force, I know the mass of the ball, and I get a big number. Okay, does that number make any sense? Well, what I did is I took that number, 80,000 meters per second squared, and I said, okay, well, in 1g, I have 9.8 meters per second squared. So that says that the acceleration of the ball is about 8,000 Gs. All right. Now, does that number make sense? Well, here you have a ball coming in at 90 miles an hour, okay, and it changes its direction, 180 degrees, okay, in 1,000th of a second, and heads out at 90 miles an hour. So that's an enormous acceleration. So imagine if you were on some planet, there's you, okay, where G for that planet was 8,163 times G of Earth. Okay, so if you were standing on a scale, you would look down, the scale would read 8,000 times your weight. All right, could you stand on that planet? No, right? You would just be flattened because your body, right, can't withstand that shape because we're mostly water. We'd be flat. All right, but if you put a ball, okay, if you put a baseball on that planet, okay, the baseball would be deformed. Where'd that go? It looks like that. Okay, so that would be the planet, right? And this thing would feel 8,000, was it 163, maybe times its weight? Okay, so the baseball couldn't stay perfectly, couldn't stay perfectly spherical. Couldn't be like that. Okay, so the baseball would actually deform because the baseball's not perfectly rigid, right? It's got string, it's got rubber bands in there. Okay, so it's not like a solid metal object. All right, so that would make sense that it has such a huge acceleration and such a huge force on it that it no longer can remain spherical.